So today's class is Computer Organization, Module 3, Lecture 1. Now, in this lecture, we will learn about the memory organization in a computer architecture. We know that in a computer system, there are mainly three types of memory. I have already discussed in the introduction part and in the addressing mode part, that there are mainly three types of memory. First one is the internal memory or registers. Second one is the main memory, and third one is the secondary memory. Clear? These are the mainly three types of memory. Now, what is internal memory? Though you already know about it, still I am just repeating the things. Internal memory are used for executing different operations in a CPU. Remember that internal memory or register is within the CPU. Okay, and this memory, the distance of the memories is nearest from the CPU. Clear? Now mainly there are two types of registers. One is general purpose registers and another is the special purpose register. Now what is the function of general purpose register? The function of general purpose register to store any data which is used for arithmetical or logical operation. And what is special purpose register? Special purpose register, you know, the special purpose register cannot be accessed by the programmer. It is only used for the architecture, for the special operation of the architecture. The example is, some of the example is program counter. That means the PC. What is the function of the PC? Function of the PC to store the address of the next instruction to be fetched. Then comes, there are the another type of special purpose register, MAR. That is a memory address register, which stores the address of the instruction to be executed. Then comes the MDR, memory data register, which stores the data of the particular instruction. Then comes the IR. IR is another type of special purpose register, which stores the instruction, particular instruction before the decoding. So these are the special purpose register. And you know that in the general purpose register, there may be different number of the register. Generally, for writing the assemblable code, suppose we are writing add A, B, that means we are adding two numbers which is stored into the register A and B. Here A and B is the general purpose register. So these are the internal memory of any computer architecture. Clear? And remember that the speed of the internal memory is the highest among all the memories in the system. Again, I am repeating, the speed of the registers is the highest among all the memories in the system. After the internal memory, then comes the primary memory. Clear? Now, what is the primary memory? For execution of any program, the program has to be stored into the primary memory or RAM. Clear? Suppose for execution of, suppose you have written one program which you want to run, processor will store the program into the RAM first, then it can execute. Similarly, operating system, this is also a special type of software that is called a system software. To run the operating system, a part of the operating system is stored into the primary memory or RAM. RAM is very important for execution of any program. Clear? Without RAM, it is not possible to run any program in a system. Now, here see the total architecture or memory hierarchy of a system. Clear? Now see from the left hand side. Here, this is the CPU. CPU contains a number of registers. This is a register, this one, all of the registers. They may be general purpose register or they may be special purpose register. Clear? Speed of the registers is the highest among all the memories in the system. I have already told you. After the registers, then comes the main memory. I will tell about cache memory later. First, you see, this is the main memory. See, the distance between the CPU and the main memory is more than that of the registers. Obviously, main memory is slower than that of the CPU and the register. Clear? Why slower? Because whenever program is stored into the main memory, there is some access time. That means processor has to access the data from the memory, and the access time is high. Remember that processor will be slowed because processor ultimately has to take the data from the main memory, because main memory stores the program to be executed. Clear? One thing about the main memory, main memory is sometimes called a RAM. That means a random access memory. Clear? Main memory is also volatile. What is the meaning of volatile? Volatile means, suppose you have written a program and the program is stored into the main memory. If power is down or power is off, then the data which is written in the main memory will be vanished, clear, or will be erased. So this is a volatile type of the memory, though this is a very high speed memory, clear. And this main memory is called the random access memory. What is the meaning of random access? Remember, in a memory system, from access point of view, there are two types of access. One is called the random access, another is called the sequential access. Here in the main memory or in the secondary memory, all the data written in a sequential manner. That means first, this is the 0 position, 0 data, then 1, then 2, then 3, up to nth position. Okay. But here also in the secondary memory, data is written in a sequential fashion because there is an address related with the each data. I have already told you. Without address, processor cannot access the data. Clear? Now the thing is, this main memory is a high-speed memory. Memory can be accessed sequentially means, suppose you have to access the fifth data, you have to start accessing from the first data. That means you have to access first data. Suppose I am not calling it data, I call it suppose memory location. That means suppose you want to access fifth memory location. You have to access first the 0th memory location, then first, then second, then fourth, then you can access the fifth. This type of accessing is called a sequential access. Clear? And this sequential access happens in a secondary memory. And remember, sequential access takes more time, because if you want to access the 100 data, you have to access all the from 1 to 99 data. So sequential access is slow. Then there is another access that is called the random access. What is random access? Random access is the access where the time required to access any data is independent of the position of the data. That means whatever time required to access the address location 0, the same time will be required to access the address location 100. Clear? Suppose time required to access the address location 0 is 5 nanosecond. The time required for access the 100 address location will also be 10 nanosecond. Clear? That means the time will be same. How it is possible? Possible because here all the memory locations are accessed parallelly. Clear? At the same time, they are accessed and find out whether the address is matched. If the address is matched, they will access the particular data. They don't have to go from the first to last. So this is called a sequential access. Obviously, the speed up of the sequential access, this is called a random access. Obviously, the time required for random access will be minimum. So speed of random access memory will be minimum. Clear? And this is the secondary memory. Speed for accessing the secondary memory will be more because this is a sequential access. The example of the secondary memory is suppose magnetic tape or hard disk. All are the sequential or semi-sequential access. Clear? Not at all they are the random access. But this main memory is always random access. So for this reason, this is called a random access memory. Remember that I have already told you another type of memory, that is the ROM. ROM is read-only memory. That is not a volatile memory, where BIOS data can be stored by the manufacturer and you cannot change the data. But the access is also random access here because ROM is a high-speed memory again. So access in the ROM is not sequential, that is the random access. Remember, clear? So these are the mainly three types of memory. I have already told this is the internal memories, that means the register. These are called the main memory where the program is stored, and where the original files are stored, that is called the secondary memory. Here all the big files are stored. Clear? Now the problem with this main memory and this CPU is that I have already told main memory is slower than that of the CPU. Clear? So the problem is, whenever any arithmetic or logical operation CPU has to do, CPU has to transfer the data from this main memory to the registers. Clear? But if main memory is very slow, what will happen? CPU has to wait until the data is reached into the register. Clear? So that is a problematic thing. Okay, it will slow the whole system. So to solve the problem, what happens? One temporary memory is stored in between. See here, in between the main memory, this is the main memory, and CPU. And this temporary high-speed memory is called a cache memory. Clear? Again, I am telling, to bridge the speed gap between the main memory and the CPU, one temporary high-speed memory is stored, that is called a cache memory. Now, cache memory, what happens in the cache memory? A small amount of data will be stored from the main memory to the cache memory. Clear? Whenever there is a requirement of data by the CPU for execution, it will take the data not from the main memory but directly from the cache memory. And the speed of the cache memory is almost equal to the speed of the register or the CPU. So CPU don't have to wait for the data. Clear? So the total system performance will be up, because it will not, because this is a high speed memory, you don't have to wait, there is a less waiting time, so performance of the system will be high. Clear? So this is the temporary memory is used for the cache memory. Cache memory, remember, the speed of the cache memory is more than that of the main memory. Clear? There are mainly two types of cache, two or three types of cache. They are called the L1 cache and L2 cache, L3 cache. That means level 1, level 2, level 3. Level 1 cache is generally called the on chip, that is, it is in the same chip with the processor. Clear? It is in the same chip with the processor. And outside the CPU, there may be L2 cache, level 2 cache, and level 3 cache. So this is the total memory hierarchy. In between these two, main memory and secondary memory, you see here, from the in between the CPU and main memory, there is a temporary memory that is called a cache memory. But in between main memory and secondary memory, there is another concept of memory. Remember, this is not a memory in the hardware, this is only the concept of the memory. That concept is called a virtual memory. What happens in the virtual memory? In the virtual memory, a part of the program is stored in the main memory, and another part of the program is stored in the secondary memory. Whenever there is a requirement to execute the data, because CPU only execute a block of data, CPU cannot execute the total program at the time. Whenever there is a requirement to execute the data, CPU will bring the data from secondary memory to the main memory, then it will execute. And whenever there is no requirement to execute a particular data, it will bring the data from main memory again to the secondary memory. Okay, but suppose you are a programmer, you will think that the total program is running into the main memory, but that is not the case. In this case, the secondary memory acts as an extension of the primary memory, which helps to execute any program after putting the program into the main memory. And if there is no requirement, again the memory will be bring back from the main memory to the secondary memory. So this operation sometimes is called the swap in. Swap in means transferring the data or instruction from the secondary memory to the main memory, and swap out means transferring the data from the main memory to the secondary memory. So in this way, this operation is executed, and programmer will think that total program is running in the main memory. So this concept, because main memory is very small compared to the secondary memory, so as programmer it is thinking that the total operation is doing in the main memory, processor is doing in the main memory. So he will think that though the main memory size is very low, he is running a large amount of program into the main memory. So that is actually the virtual memory. Yeah, I will tell later about that. There is a whole lecture about the virtual memory. Then I will tell later more about the virtual memory. So this is the virtual memory. Remember that these all memories, internal memory, cache memory, main memory, secondary memory, they all have the existence, that they are the hardware device. But this virtual memory is not a device, it is a concept. This concept is actually executed with the help of the operating system. And remember, then in the memory hierarchy, this is the speed is the highest, so cost is the highest. Speed directly varies with the cost. If the speed is high, cost will be high. Then comes the cache memory. Cache memory cost is higher than that of the main memory. Speed is also high than that of the main memory. Then comes the main memory. Main memory cost is high than the secondary memory, low than that of the cache memory. Okay. Similarly, speed is also high than that of the secondary memory. So this is called the total memory hierarchy in the computer organization system. Now, this is the main division of the memory. See here, memory is divided into primary and secondary. These are the division. Primary memory can be divided into RAM, ROM, read-only memory, where you can only put the data, you cannot erase the data easily. And RAM is a volatile memory. RAM can be divided into SRAM and DRAM, and ROM can be divided into PROM, EROM, and EEPROM. What is this different? What are the division? I will tell in the next slides. So types of the ROM. Though you know that ROM, once you put the data into the ROM, you cannot delete the data, but still there are programmable ROM. What is the programmable ROM? In the programmable ROM, manufacturer can program the particular instruction or particular code, and it is a one-time programmable. Once you program, you cannot delete the program. So that is called the programmable ROM. Then number 2 is the EPROM, erasable programmable ROM. Here read and written electrically like the PROM. Okay, but here the contents can be erased multiple times. Clear? Whatever the content, it can be erased, but this erasing the content is not so easy. It has to expose to the ultraviolet light, and in the ultraviolet light, all the contents would be deleted in the EPROM. This is also programmable, but it is erasable. Clear? Ultraviolet ray can erase the ROM. Then comes the EEPROM. Here, this is the electrically erasable programmable ROM. The difference is here, instead of the ultraviolet light, some electric pulse is used to write the program and to erase the program. Here no ultraviolet is written. And another major difference is there that here data can be written without erasing the prior contents. That means whatever data it is written, okay, you can erase particular data without deleting all the data here, but which is not possible in the EPROM. Once you export into the ultraviolet ray, it will, whole the system will be deleted, whole the data will be deleted. So these are the different types of the ROM. Then types of the RAM. Types of the RAM, mainly there are two types of RAM. Clear? One is called the dynamic RAM and another is called the SRAM or the static RAM. What happens in the dynamic RAM? In the dynamic RAM is actually made up with the capacitors. Okay, the presence or absence of the charge in the capacitor is treated as a 0 or 1. If the charge is present, it is considered as a 1, otherwise it is considered as a 0. So using the capacitor or bunch of capacitor, the DRAM is made. Okay, the device is less costly and it is very smaller in size, so it is a denser. That means the size of the DRAM is very small. Clear? But it is very slow. The device is very slow because why? As charge is stored into the capacitor, time to time it has to be refreshed. Otherwise, whole charge will be vanished and it will be 0. So this refreshing of the capacitor will take some time. So DRAM is a slow device, though it is used for making the RAM or main memory. Clear? So another type of RAM is called the SRAM. Okay, that means the static RAM. Static RAM is nothing but it is made up of the traditional flip-flop. What is flip-flop? Flip-flop actually helps to store the data. In the digital logic or digital electronics, you learn more about the flip-flop. Flip-flop is a device which can store the memory. That means 0, 1 bit it can store. So this flip-flop, using this flip-flop, this stacking RAM is made. Okay, and obviously, as there is no capacitor and there is no requirement of refreshing the capacitor, this SRAM is faster than that of the DRAM. Clear? But this is not denser. Okay, and cost is obviously more than the DRAM. So obviously, these two types of RAM is used for making the memory. Now here it should be noted that cache is made up with the SRAM. Remember, static RAM, because the speed of the cache is high, and main memory is made up with the DRAM. Okay, because the speed of the DRAM is slow, so main memory is slow than that of the cache. Because as the DRAM is cost is low, you can use it for making the large main memory. But as the SRAM cost is very high, you cannot make very large memory using the SRAM. So SRAM is used only for making a small amount of cache memory. Clear? So these are the types of the RAM. After the RAM, see here how the data is stored into the RAM. Clear? In the left hand side, see here, this is, I have shown you a total RAM. Here 12, 14, A5, 17, B1, 19, A5, 80, all are written in the hexadecimal code. These are the data which is stored into the memory. Clear? And these 000, 001, 010, 011, these are the address of the particular location. That means the address of the 12 is 000, address of the A5 is 010, address of the B1 is 100. See here, there are 3 bits we have used in the addressing. That means what is the total number of the address we can generate? Address generated we can generate is 2 to the power 3, that means 8. So 1, 2, 3, 4, 5, 6, 7, 8. So if the number of the address bit is n, size of the RAM or the size of the physical memory will be 2 to the power n. Here the number of the address bit is 3, so size of the RAM is 2 to the power 3, that means h. Now see, these are the specification of the bits. Sometimes you heard about the kilobits. So remember, 1 kilobits is equal to 2 to the power 10 bits. Okay, 1 megabits is equal to 2 to the power 20 bits. If I call 1 gigabits, it will be equal to 2 to the power 30 bits. Clear? So these are the address bit, and these are the specification of the number of the bits using the power of the 2. Clear? So using the address bits, we can find out what is the size of the RAM. If I told you the address bit, you can easily find out what is the size of the RAM. Clear? Now see here, this is very important. This is the description of a RAM. Now see here, I have shown you one RAM. Here in the RAM, I have written here 1K into 4. What is the meaning of 1K? 1K means, I have already told you, 1K means 1 kilobits. So that means what is the total number of bits? 2 to the power 10 bits. So here if I write 1K, that means 1 into 2 to the power 10. That means there are 2 to the power 10 bits. So what is the number of the address bit? Obviously, number of the address bit in this RAM is 10. That means if I specify one RAM and if I write 1K into 4, this left hand side 1K should be the number of the address in the RAM. So here, what is the total number of address? Total number of address is 2 to the power 10. What is the number of the address bit required for the RAM? 10 address bits are required. So see here, A0 to A9. What is the total number of address bit? 10. A0 to A9. Here it shows that this is the address of the RAM. Okay. Now why this is a slanting line given here? The meaning of the slanting line is that here A0 to A9, 10 bits, but here I have shown only one line. When I put one slanting line there, that means this is not a single wire, this is a bus. And what is the number of the wires in the bus? Number of the wires in the bus is the 10, A0 to A9. Instead of, you can write also A0, A1, A2, A3 up to 10 wires you can draw here also. So instead of 10 wires, you just draw one wire, you give one slanting line and you put these values. That means it will mention that this is a bus. It consists of 10 wires, A0 to A9. Clear? So this is for the 1K into 4. So what is the 4? This 4 is the width of the RAM. Okay, this is the height of the RAM, that means the number of the address bits in the RAM, and this is the width, that means what is the total number of the bits it can be stored here. Go to the previous example, see here. What is the width here? Here we have used the hexadecimal code and 2 bits are used here. You know that in the hexadecimal 4 bits are used, so 4 bit per 4 bit. That means here the width is 8 in this case, and the number of the address is here 8. So this is a 8 cross 8 RAM. Okay. Similarly here, this is the total width of the RAM. That means maximum 4 bit can be stored in the RAM here. Okay, so this is the data bits. Remember, this left hand side first one is the address bit, and this right hand side is the data bit. Number of the maximum data bit is the 4. Number of the bits is here 4. That means width of the bit is 4. So obviously it will be from D0 to D3, D0, D1, D2, D3. So here I have again given one wire and this slanting line, that means this is a bus. Bus consists of D0, D1, D2 and D3. So this is the specification of the RAM, which contains 1K address and width of the data is 4. So this is 1K into 4. There are two another signal, WE bar and CS bar. Okay, WE bar means write enable. This is low enable. That means when here, if you give 0 here, it will be inverted here and it will make 1, and then you can write, or processor can write any data into the RAM. So this is called write enable. That means this signal, if it is on, it will enable the RAM to write anything here. Okay, and another is called the chip select, CS bar. This is also low enable. That means when this is 1, that means if you give 0, it will be inverted here and it will be 1. In this case, this chip, particular chip, okay, this RAM will be activated. Otherwise you cannot. That means activated means you can read the data from here, but for writing the data again you have to activate this. Clear? So this will activate the whole chip and this will activate the write operation. That means if processor want to write anything, it has to activate this particular signal. Clear? So this is the definition of the RAM. In the RAM, it contains the number of the address bit, width of the data, write enable signal, and the chip select signal. So this is the total specification of a RAM. Clear? Now, one thing, suppose, see here very clearly, RAM expansion. Suppose you have a 1K into 4 RAM. It is given here. Clear? 1K into 4 RAM. Now you want to expand the RAM. See here, you have 1K into 4 RAM. This is 1K into 4. This is 1K into 4. You have to make 1K into 8 RAM using 1K into 4 RAM. 1K into 8 means here number of the address bit is the same 1K, but here the number of the data bit is 8. See here, that means width is increased. So you have only 1K into 4 RAM. That means you have to use 2 1K into 4 to make 1K into 8 RAM. Clear? So how to connect this? This connection is sometimes called a parallel connection. See here, this is 1 RAM. This is 1 RAM. Clear? A0 to A9. This is the address. This address will be applicable for this RAM and for this RAM. For both RAM, this address will be applicable. Clear? But for the data, see here. For the data, this D0 to D3, 4 bits will come from this RAM, and D4 to D7, another 4 bits will come from this RAM. So what is the total number of bits? 8 bits. So this is the 8 bits. So here write enable, it is connected with both the RAM. Here it is connected here and it is also connected here. This is chip select, it is also connected with both RAM. Now suppose you want to address is, suppose the address is 1000101011. Clear? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 address. So if I give 10 address here, suppose data 1, that means the data in this address stored at the RAM 1 is 1011, and the data stored in this address at RAM 2 is 1001. So if I give this address and if I activate the chip, which data will be activated or which data can be accessed? The data can be accessed from both from this RAM and this RAM. So that output data will be 1001. See 1001. So it will be D0 1001. This is the D2 data. Clear? And then 1011. So this 8-bit data. If you give this address, you will get the output this data. Okay, why this data you are getting? Because you have connected two RAMs while you increase the width of the data. That means you are using two 4-bit RAMs. You are getting the data as a 8-bit. Clear? So this is called a parallel connection. Okay, there is, so here we are making 1K into 8 RAM using 1K into 4 RAM. Remember, here we are increasing the width of the RAM, not the address. Address is both 1K and 1K. Clear? Next come, suppose we have to make 1K into 4K into 4 RAM using 1K into 4 RAM. What is the difference with the previous one? Previous one difference is here we are increasing the address bits, not the data bits. Here data bits is both 4 and 4. Okay, but the address bit is here 4K. Here it is 1K. Clear? So as address bit is 4K and one RAM is 1K, so 1K, 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 we require 4 RAMs because this is 4 time address. So this one, 1, 2, 3, 4. 4 RAMs are used. Now see here. This is 4K. 4K means K means 2 to the power 10. You know. And 4 means 2 to the power 2. So if I multiply this, what will happen? 2 to the power 2 into 2 to the power 10 into 2 to the power 2. That means 2 to the power 12. That means what should be the address bit in this RAM? 4K into 4 RAM? It should be 12 address bits. Okay, it should be 12. But what is the address bit here in the 1K into 4 RAM? This is the 10 address bit. So what will happen for the 2 extra address bit? See here. So this is the 4 RAMs. I connected all the address, this address with this RAM, A0 to A9. 10 address bit with this RAM, this RAM, this RAM, and this RAM. They are connected. Clear? Now, so what is the total address bit we have put here? We have put here 10 address bit. Okay. Now there are 2 address bits remaining, that is the A10 and A11. This is from A0 to A9, 10. A10 to A10, A11, these are the 2 address bits. That means the 12. So 12 address bits. Now what is the function of these 2 address bits? These 2 address bits you have to pass through a decoder. Decoder means 2:4 decoder. Okay. Those who have done decoder in the lab, you know the decoder. Otherwise, just listen. The decoder means if you give 0, 0, the first line will be activated. If you give 0, 1, the second line will be activated. 1, 0, third line, 1, 1, fourth line will be activated. Clear? Now see here what happens if I do this type of operation. See here. Suppose this is the address. What is the total number of bits in the address? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2 to the power 12. So 12 address bits. Suppose this is the address. Clear? Now here the data. Suppose this is the address and the data which is stored in the data 1 at the particular this address, because the 10 address is required for each RAM. So this 10 address, in this address, RAM 1 stores 1011, RAM 2 stores 1001, RAM 3 stores 1000, and RAM 4 stores 0011. Only for these 10 addresses, not for these 2. Okay, now what is the function of these 2? See here. If processor gives this type of address, first it will go to this left hand side 2 bits. Okay, this is the A0 and A11. Okay, that is called the most significant bit positions. What will happen? It will pass the most significant bit position into the decoder. If it pass the data into the decoder, what will happen? This is 1, 0. So 0, 0, first line will be activated. 0, 1, second line. 1, 0, third line will be activated. That means here this is the CS chip select. This chip select line is shorted with this activation line, so it will go to this. That means this chip will be selected. If this chip will be selected, that means third RAM is selected. So what is the data in the third RAM? Data in the third RAM is 1000. So output data will be 1000. Clear? That means this extra 2-bit is used actually for selecting the one RAM out of the 4 RAMs here, because you are using the 2:4 and it is shorted with the chip select line, and write enable is connected with all the data here. Okay. So depending on these two most significant bits, it will choose. If it is 00, it will choose this RAM. It is 01, it will choose this RAM. It is 10, it will choose this RAM, and 11, it will choose this RAM. So this is called a series connection, and this is another type of RAM expansion. Clear? So thank you. This is all for today.